All right, welcome back to pycse. Today I want to talk about some times when root fails, root from scipy.optimize for solving nonlinear algebraic equations. And I'll start out by reminding you how to use root when it does work, but the rest of the video will talk about when it doesn't work. So root is a function in scipy that is used to solve nonlinear algebraic equations. All right, sorry about that. So here is an example. Let's say we want to solve e to the x equals 2. Then we might write, well, first we'll import a bunch of things. Then we define a function, def f of x. And here we're going to return np.exp of x minus 2. All right, so this is going to be equal to 0 when e to the x equals 2. And then to solve this, we import the root function. And then we just call it root. We provide our function f, and we give it an initial guess. Let's say we guess 1. And this, when it works, gives us a status of 1 and a success of true, and gives us the solution at x. And this is about log 2, which is the right answer. So normally things work that well, and we don't really have to think about it. But there are 4 scenarios I'll talk about today where it doesn't work, and we're going to look at them one at a time. So one is when there's just no solution. Right? If there's no solution, it would be remarkable if root found one, and it doesn't because it doesn't do magic. But we'll just look at an example just to illustrate what happens when that happens, so you'll recognize it when you see it. So let's define the function, another function f of x, and let's make it x squared plus 1. Now, by inspection, you might note there is no real number that will make this function be 0. Of course, x could be the I, and I squared is minus 1, but root only gives you real number solutions. So there is no solution here. This function never intersects the 0. And if we try to find one, let's say 0 is about as close as you can get, then we get an error or a message that the iteration is not making good progress. It has gotten stuck, and it is staying at the answer that you put here. And it doesn't matter what we put here. It basically tries to go down to 0, and then it's stuck. It can't go any lower, and that's because at 0 it's equal to 1, and there's nothing that can happen. There is no solution to this problem because this function does not have a 0, and you just can't find it. But this is what it looks like, and here we get a status of 5 that is corresponding to this message. All right, how about another example? Another place where you can run into trouble is what I'll call pathological tolerance. So remember that when root works, it is iterating towards the solution, and it stops when it thinks that it is close enough to 0. So let's take a look at a function, and this one is a pathological function in a way. So let's make a linspace x.linspace from minus 1 to 1, and then let's make a plot of x to the 7th. All right, so that looks like this. And what you can see is in this whole region here, it is basically 0. And that's because you have small numbers, and small numbers to the 7th power are small numbers, even smaller. So if we try to find where is the root of x to the 7th, we're going to run into some difficulties. And I'll show you what that difficulty looks like here. So let's do f of x again and return x to the 7th. And now let's look at the root of f, and let's make a guess of 0.1 and see what we get. What you find is that we get a new error that the number of calls to function has reached the maximum function evaluation. Now, I find this one a little bit surprising because this number is basically 0, but we're not getting a status of 1, we're getting a status of 2, and it's claiming it did not succeed. And part of the problem is that it has to take more than 400 steps to figure out, that it's making progress. And sometimes you can fix this by changing the solver. So the default solver is called hybrid, HYBR, but we can change it to something like Broyden here. Broyden 1. And if we do that, then it tells us that a solution was found at the specified tolerance. But look where the solution is, 0.09. It's basically near the guess that we made, right? And if you do this, you'll get different numbers that tell you that a solution was found at the specified tolerance. And that's what's illustrated here, that 0.2 to the 7th power is probably about this number, and that is the tolerance in which we define the 0 to be. So you have to be really careful when you look at answers like this and ask, what is the range in which the 0 is kind of close here? And if we look here, it's quite large, right? It's not easy to see how much of this is maybe we can try this. Plot.ylim. Let's do 1e minus 5 and 1e minus 5. So we'll look at negative 1e minus 5 to positive 1e minus 5. And there is a whole range. Oop, that should be minus, not 11. A whole range in here where this is from about, I don't know, negative 0.2 to 0.2, where all of these might be considered 0 at some tolerance level. Now this is a particularly pathological example, but one that you may come across in some functions where there are regions that are really flat. So we'll come back to this flat region problem in the next example. All right, let's take another look now at what I'll call a pathological initial guess. So here, again, let's start with defining a function. And I'm going to define a polynomial, x cubed minus 2 times x plus 2. Seems like a pretty simple polynomial. And then let's make a plot and see what we're looking at. Let's say for minus 2 to 2. And we'll look at x and f of x now. Let's see, what did I type wrong? Oh, we should return this. All right, so very simple looking polynomial. You can see one root over here and no other roots. So there's only one answer in here. But now if we make, and maybe let's do something, now that we know where the root is, if I ask for root of f and I guess minus 2, then not surprisingly, we get a good answer that looks like this. But let's say you weren't careful and you didn't make the plot and you just guessed, oh, maybe x equals 0. Now we find that we don't get an answer. We get again, iteration is not making good progress, and it's giving us a false and a status of 5. So what's happening? Well, if we look at 0, we have right here, qualitatively what's going to happen is the derivative here is minus 1. So if we take this and kind of extrapolate back to the origin, like in the Newton's method, and then come back up here, now we have a point here where the slope is probably like, looks like about 2. And so if you come here and go back down to the 0 and come back up, you just end up kind of bouncing back around in this region forever. And so you get stuck in a well where all you do is kind of bounce back and forth like this until it says, hey, I'm not making any progress. It's just not going to work. And it's not just 0. I think many of these problems exist in a whole range. Like there's a whole range of space in here where you're just going to bounce back and forth between these two and never make it out. All right. So that is just a feature of the iterative steps, and the only solution is that you have to make a better guess. You can also change the solver sometimes. So if you use a solver that does not use the derivative, so like df is one that doesn't require the derivative. The df is for derivative free. Then we usually will get a good answer here that is the right thing. So sometimes you can get out of this by changing the solver. Sometimes you should change the original initial guess. All right, that was the third example, and the final one we'll look at is vanishing gradients. So the problem here is related to when the solution is very flat, and that is that when the solution is very flat, the derivatives go to 0, and it's not possible to get good progress. So let's look at a simple example here. So let's do def f of x again, and we'll just look at the tan h. Tan h is often used as an activation function in neural nets. And if we look at what it looks like, let's look at np.linspace minus 20 to 20. Plot x comma f of x. We have this kind of classic sigmoid shape where it plateaus at -1, goes up, intersects with the at 0 at one place at 0, and then it goes up here and goes flat. So the root of this is just 0. That's it. And if we make a reasonable guess, I don't know, like even 1, anywhere from plus or minus 1, then you get that we get a true answer, a true success, and it converges right to 0. But if you make a bad guess like 20, then you find out that you can't make good progress. And what's happening is way out here at 20, the function is so flat that even when it's taking little iterations, it isn't able to eventually get downhill like this. And this is a known problem in machine learning when you're training neural nets, that the gradients vanish out here. And so for very large x, you're not able to optimize the weights. So 20 gives this, 19 gives the same result, but I think by 18 there's enough gradient that it is eventually able to converge. So this is another place where you want to avoid choosing places where the gradient is too large. All right, and so that's the summary, the main ways that you can have failures of finding nonlinear algebra solutions. They are places where there's no solution. Maybe the equations are poorly formulated or missing some information. We talked about pathological tolerance, where there might be a whole region where the solution is basically equal to 0. We have pathological initial guesses that lead to infinite loops. And we have vanishing gradients that, for some algorithms, prevent you from making progress. So let's see if we change the solver here. Maybe it will be, again, possible to recover it. In this case, it isn't possible. You get too many function evaluations for this one. And let's just try a couple of others. Same for this. That one's the same. Let's see. I don't know if any of these, I'm not real familiar with what these are. Would just be like trying things. Let's see. Anderson. So I guess the answer here is that you have to make a better initial guess. Okay, so this one, you really just need a better initial guess that doesn't have a vanishing gradient. All right, so that's it for root failures. Hopefully the audio is a little bit better in this one. I discovered there was an extra microphone recording in previous videos that made it sound kind of echoey or underwater or something. So hopefully this one is better. And if it is, drop me a note and let me know. And if you like this video, feel free to subscribe to the channel and let me know what you're interested in. Thanks, and